like you had, for recording you had a separate big device. For making a phone call you had a standalone, either a mobile or some kind of electronic device, and for doing a photography, for doing as a GPS system. So these were complete discrete system, and you never had something like a mini computer within your mobile phones, which is now what you call a smartphone, which almost incorporates every different types of electronic items which were bulky in size, bulky and bigger in size, as well as the performance were not up to the mark. By performance, essentially, what I mean is in terms of either in terms of signal processing or in terms of any kind of processing. So the processing power of the microprocessor or the memory that was attached at different levels was not up to the mark. And as time has progressed, because of this miniaturization of transistor, it has been facilitated. And then we also talked about the two major ways in which the industry or the semiconductor uh, engineers and scientists followed to scale down the transistors. So it did not. So those were like having constant voltage scaling and constant field scaling. But at a later stage, there was a kind of a mixed bag of the two type of approaches, which was uh, pursued to achieve the better performance of transistors. So the improvement in the performance was not only confined to the transistors, but also at various levels of your overall chip. So right from transistor level to the gate level to your circuit level to your system level, and so on and so forth. So everywhere there was a constant, you can say, constant R&D to find out ways to improve the overall performance of your devices. So nowadays you're seeing more and more of these things. Even sensors are included, and that is how you are able to monitor a lot of these health monitoring machines within the same chip area, and that is why your the new smart watches or smart devices are all coming in the same small chip area. So maybe 20 or 30 years down the line, the watches were not having these chip, but they may be having a bulky and a large discrete device to say monitor your blood pressure. But nowadays, or your pulse rate. But nowadays, it is all in your small sized smart watches. So basically, the whole idea is to continuously improve upon the transistor size and its various performance parameters, but also to improve upon the gate level, the circuit level part of it. So, like last time, I think. So that is very important, knowing about the secondary effects of your transistor, as well as what are the effects that are coming due to continuous scaling down, which has facilitated the so-called next generation of your semiconductor or VLSI industry. So when we are talking of this thing, we kind of did a build up about how to make the so-called universal gates out of this transistors, starting with the NOT gate, and the NOT gate actually facilitated us to kind of make NAND and NOR gates, and just by series and parallel combination of your PMOS and NMOS and its internal properties, we were able to realize any kind of combination of sequential circuits or any kind of a Boolean expression. So once we were able to uh, uh, once we were able to appreciate this, then we went on to understand the basics of your of the fundamental block of building all these circuits, which happens to be your CMOS device, which is essentially an inverter. So that led us to kind of go deeper into the understanding of your inverter. And we talked about the inverter in all the different type of stages. It's just a moment. Its functionality and basically the transfer characteristics. And so we saw in three modes of operation. The first one was static. The second one essentially was the dynamic, and then the third one we have already talked about, which was the short circuit part. Uh, so sorry, the short circuit part came actually into the power dissipation. So once we talked about the static and dynamic behavior, then we talked about the power dissipation of these inverters, and uh, I think that was the time we kind of finished in our last class. So I would like to finish that part, and then go to the introduction of HTL. So how do you implement all these things? We will take very few examples, and that will give you a brief description of how to actually go and implement that on a hardware description language. So we will be focusing mostly on the Verilog part. So is this visible? So today we need to do power analysis of the inverter. We also talked about one stage inverter, then cascaded inverter, which is a two-stage inverter, and then a chain of inverters with probably having many folds of fanouts. So we also tried to understand different aspects of inverter and went into detail, but we did not talk about the power analysis of simple inverter, and that is why we need to finish with that part. Before that, one needs to know the basic um, definitions of energy and power. So energy, we have gone through this slide, but just trying to repeat few things. So energy is measured in joules or kilowatt hour, and it's a measure of ability of the system to do work or produce a change. So what is power? It's measured in watts or the kilowatt. It's the amount of energy required to given unit of time. So the important thing is to know what exactly is average power, because some of these things we shall be using while determination of energy and power in our inverter configuration. So average power is the average amount of energy consumed per unit time, and instantaneous power is the energy consumed if the time unit goes to zero. So from So this is instantaneous power is important thing uh, which we probably would be using in our course of inverter analysis with respect to in the course of power analysis for our inverter configuration. So instantaneous electric power uh, PT is VT times I of T. So where VT is the potential difference across the component and IT is the current through that component at that particular time T. Okay, and electrical energy is defined like this. So the important thing that one needs to determine the uh, is that electrical energy in CMOS circuit is equal to the power times your delay. Okay, so this delay basically is an important parameter which we have already determined while we were doing the dynamic behavior of inverters. So power is drawn from a voltage source attached to VDD pins of a chip. So the instantaneous power is defined as this. Please note down these things. Energy is defined as the differential of power with respect to t integrated over from 0 to time t, and the average power is energy per unit time, which is, as you can see in the expression, 1 upon t. So integral 0 to t IDD at instantaneous time t times VDD into your dt. Yeah, so essentially you are having three types of analysis. I think the first one is your DC analysis, in which you're either having the state 0 or state 1. Then you have AC analysis, in which it can be any sine function, A sine omega t or A cos omega t, and then you have a transient kind of analysis in which there is at a very short time you have transient from 0 to 1 or 1 to, so some kind of an impulse for a very small time, so that kind of thing. So here if you see in this slide, I hope the slide is remember this these slides are from the professor from IIT Roorkee. So if anything you want to go back and see, you can actually see them, or otherwise you can come back to me, and if there's any difficulty, you can just have a word. But this slides I'm taking for your convenience so that you are able to go back and study them if required. I hopefully think those who are present, they may not be requiring, but especially for those who kind of skip and then try to only come in the final examination. So uh, we need to also define two more parameters, I think, which is your fall time and the rise time. So fall time is the time that it takes for your VDD to fall from 90% to 10%, and the rise time is the time taken for your voltage to rise from 10% to 90% of your VDD. So this basically gives the energy consumption which is proportional to capacitive load. Why? Basically, as I mentioned, if there is a direct connection between your VDD and your load capacitance CL, then this load capacitance would be charge and discharge um, faster if your VDD is higher, and vice versa. So that is why it becomes very critical, the value of VDD as well as the rising in the charging and discharging of the capacitor. Remember, charging and discharging in a capacitor happens uh, and has a exponential behavior. You must have studied that before. So this is talking about the other half, which is the discharging part. So charging and discharging of the capacitor basically helps you to have two situations. In the first situation, uh, for energy and instantaneous power, if uh, you have an inverter 1 and inverter 2, so there will be high instantaneous power if the W by L, which is the width to length, which is also called as the aspect ratio of your inverter 1, is faster than the W by L of inverter 2. Okay, so this will be basically because inverter 1 charging would be faster with respect to inverter 2. So this is another important parameter where the width to length ratio of your transistors would play a major part to define your instantaneous path. Okay, so you can have high instantaneous power when your W by L is greater than any reference inverter, and it may have a lower instantaneous power if W by L is smaller. So it basically defines the instantaneous power. So W by L, which is the width to length, which is there in your basic transistor equations. If you just go through your transistor equation, you have W by L. So that W by L ratio, which is width to length ratio of your transistor, plays a major role to define whether the instantaneous power that you would be able to achieve through the inverter would be high or low. And it would also let you know whether the inverter 1 is faster or slower. Similarly, for the W by L of the pull down network. So initially we showed the W by L for your PMOS and W by L for your NMOS. So both these W by L, when compared to another set of your inverter, can help you to redefine or regulate the instantaneous power, okay, to make it either high or low. So in the energy power matrix curve, which is basically energy is in watts, and this graph basically is between uh, energy and time. So here you can see by approach 1 and by approach 2, the energy is the same in both the cases. The energy, the total energy, whether in approach 1 or approach 2, does not change, but it is the amount of power and the time duration which is different in both the cases, as in whether you are whether you go for approach 1 or whether you uh, whether you go for approach 2. So energy is equal to power times the time for calculation, which is power into delay. And delay, as we know, is in an inverter configuration is dependent on many other parameters which we have determined and studied in our previous classes. So energy calculation for 0 to 1 output is shown in this graph. So it is this whole is to understand what happens in a inverter. So energy dissipation determines the is a very important parameter, as it determines the battery life in number of hours and also sets the packaging limit. So basically, you're talking about how many module of combination or sequential circuits can be placed in a chip and how many interconnects are required. That would be ultimately defined by what is the overall energy that is getting dissipated by the chip. We define another important parameter, which is the peak power, that determines the power ground wiring designs. So, and it impacts the signal to noise margin and other reliability aspects. So energy dissipation and peak power are very critical when you are designing either an inverter or any kind of higher order combinational sequential circuits. Say for example a multiplexer, say for example a multiplier, say for example mm, um, say for example a latch, say for example a counter. So and then your complexity becomes much goes to a much higher level, and you need to do the energy dissipation and peak power determination before you actually send your design for for fabrication in a semiconductor fab industry, which is also called as your fabs. So where does the power go in the CMOS? So essentially there are three types of power dissipation. One is your dynamic power consumption, okay, which is essentially due to the charging and discharging of your load capacitance. Remember, you also need to keep a check on the load capacitance, which can be which constitutes of many parameters if you have a relay of such inverters. So overall load capacitance kind of have various components, not only from your initial stage but also from the next stage. Then you have the so-called short circuit current. So short circuit path between supply rails during switching. Okay. So remember, what is the short circuit current? It is essentially when both, it is a situation in which in an inverter configuration, both your PMOS and your NMOS transistor are in the conducting state. So there is essentially what you call as the direct path between, there is a direct path between your VDD and the ground. And then you have the third component, which is essentially the leakage kind of current. So this leakage current is basically leaking of the different types of diode. Remember, a transistor is essentially an extension of your diode. So you have different types of internal diodes that is formed within the transistor system or transistor configuration. So there's a leakage that is almost happening all the time in your diodes and transistors within the circuits. So what is this leakage? This leakage essentially is majorly of two types. One is when your uh, when your VDD is less than threshold voltage, then ideally you should not have formed any kind of a channel. So if there is no channel, there would be probably no current. But still there is a kind of a current which is what you call as the subthreshold current, that is also called as the leakage current, that is there in your transistor device, also in your diode configuration. So most of the times when we are studying this VLSI design, we start with the very basic that ideally speaking, the channel will only form between your source and drain once you achieve voltage higher than your threshold voltage. And remember, at the initial stage, I asked you to determine the threshold voltage of a transistor. But so the current conduction would only happen when the voltage that you give is higher than that of your threshold voltage. So what happens below threshold voltage? Is there no current that is going? The answer is no. There is still some current that is flowing, and that current is leakage current. So that needs to be avoided or mitigated or minimized. So this leakage current happens to be one of the component of the overall current, though its value maybe 3 to 4 order lesser than the current that is flowing when the complete channel is formed. And this is also called as your sub-threshold current. Sub-threshold means current that is flowing within the transistor system when you have yet to, when you have not achieved the optimum threshold voltage. That means the channel formation has not actually occurred. Okay. The other type is of leakage current is because of again the transistor property, or even probably the internal diode property, uh, but mostly we have talked in transistor. Since it is a MOSFET kind of a configuration, you have oxide which is actually acting as a gate dielectric. So these gate dielectrics are very thin, and so there is a huge probability when you increase the overall field because of the increase in the voltage for some current to leak out from the gate to your source and drain. So that is the other type of leakage current. Yeah. So if we let's talk about a bit detail about these three uh, dynamic these three type of power consumptions. For the first one is your dynamic power. So this is the major part. So we've already talked about the dynamic behavior. So the power in this is defined as and is equal to the load capacitance CL times the VDD, where times your frequency, where the power is going from 0 to 1. Okay, so this is the power that is happening when you are having a transition from 0 to 1 stage. So P01 is the probability for 0 to 1 switch of the output. F is the frequency, and alpha is the activity factor. Okay, so how so alpha we will be also defining at a later stage. We will be giving some insight to alpha at a later stage. What do you mean by activity? So frequency you would already be knowing. It is like, you know, going so I think, yeah, so this dynamic power consumption is actually uh, data depend is also data uh, so is also having a component where the switching activity is a function of your data, and that it is basically because the frequency can be of this nature or the nature below. I mean, like any nature which is either 0 1 0 1 0 1 0 1 0 1 or 0 0 1 1 0 0 1 1 or 0 1 0 1. So that kind of, so basically it is on the data that is coming as a part of your frequencies. What is the nature? In fact, data basically is the nature of your frequency. Yeah, something like this. And the activity factor is like in a clock pulse. So this is a clock pulse. So it is there's a rise time and a fall time in this clock pulse. So here you are seeing 8 pulses, 1, 2, 3, 4, 5, 6, 7, 8, and you have another parameter which in the same time clock you are having fall time or rise time happening at 4 times. So this like 1, 2, 3, 4. So here you are seeing a transition from 0 to 1. Similarly, if you check out here, it is a transition from 1 to 0. So your activity factor is number of transitions from 0 to 1 in per number of clock pulse. So that is your activity factor. Are you there in the class? Class? Yeah, okay, fine. So the other type of consumption is your short circuit power consumption. So I've already told you that if you talk about an inverter, it has basically 5 regions of operation. So we are talking, when we are talking about short circuit power consumption, we are actually talking of a very peculiar state in this inverter where both your PMOS and your NMOS, remember, both your PMOS and your NMOS are in on state or what you call as the conducting state together at the same time. Okay, so that basically has makes a direct link between the VDD and the ground. So there is a direct link because both the transistors, it may be for a very small time, but it does exist. So that basically leads to power consumption or power dissipation. So this situation in which both the transistors are in the on state together would lead to a direct path between the VDD and ground, and there would be a leakage automatically. So this is what you define as the short circuit power consumption or power dissipation. So this happens during the switching. NMOS and PMOS are conducting for a very short period of time, which is what you call as the short circuit time. And there is a direct path between the VDD and ground. So the power that is consumed in this stage is basically defined as the VDD times your short circuit current, and this happens when you have a transition from or switching from 0 to 1 or 1 to 0. So it will be talking in it would be adding this switching activity where both the transistors are in the conducting state in both the transition, whether the transition is going from 0 to 1 or 1 to 0. Your overall short circuit power would constitute both parts. Yeah. So if when you have seen that VTC curve, it is talking about this stage in which both NMOS and PMOS are in the saturation state, and there you are having a, ideally speaking, Vin is equal to VDD by, yeah. Now the third type of power consumption, which is the leakage power. I think I did mention it has majorly the two component. So the first one is your subthreshold leakage. Hello, is it visible, class?
Yes, sir.
Okay, so it has two major components or the important components. One is the subthreshold leakage. As we have already mentioned, it is the current that is flowing when the channel is not actually formed, or when the voltage is less than your threshold voltage. The other one is the gate oxide leakage, and that is essentially because of the leakage that is happening between the gate to your source or gate to drain. Similarly, so it would have four components in an inverter configuration. So this is an inverter configuration. So subthreshold leakage is the leakage that is happening even when there is no voltage supply. Even when there is no voltage supply. That means that the voltage is less than your threshold voltage. So remember, when you apply a voltage, it starts to form a channel and starts to conduct only and only when the voltage is greater than threshold voltage. That is, threshold voltage is the voltage beyond which there is a channel formation, which facilitates the current to. Hello, who's this? Okay, which facilitates the electrons or holes, or basically the current, to move between either source to drain or drain to source. Okay, depending upon whether it's a PMOS or a NMOS type of transistor. So any current that is flowing below that is what you call as the subthreshold current, below this threshold voltage. But the order or the magnitude of this subthreshold current is almost 3 to 4 orders lower than the normal current that you see. If suppose if the normal current is milliamperes, so this may range from pico to nanoamperes. That is 10 to power 12 minus 12 to 10 to power minus 9. When the normal current is, say, milliamperes, which is, oh, sorry, microamperes, which is 10 to power minus 6. So it may have around 10 to power minus 3 to 10 to power minus 6 difference with respect to your normal current. So subthreshold current, the value though being small, but since we are talking a huge number of transistors in VLSI circuits, this becomes an important component. So initially, in earlier times, the number of transistors were a few thousands or million. Now it's going beyond billion, which is beyond 10 to power 9 transistors. So then this becomes a problem because the leakage also increases, or the leakage, overall leakage current increases if you consider the overall circuits per unit chip, or overall transistor per unit chip area. Okay, and the other part is your gate oxide leakage. So gate oxide leakage is happening between the gate and source and drain for your NMOS transistor, as well as gate and source and drain for your PMOS transistor. So it has four components in an inverter configuration. Okay, so the overall leakage power is defined as I leakage into the PDD. So I leakage would has both the subthreshold leakage plus the gate leakage times your VDD. So your power equation, power consumption has is the sum total of all the three components, which is dynamic power, short circuit power, and the leakage power. So generally you have dynamic power, which is having the major component 40 to 70%, but it is decreasing by the day. Similarly, your short circuit power is of the order of 10%, and it is also decreasing by the day. I mean, like, there are engineers and scientists working to improve on all these types of power consumption, because at the end of the day, ideally speaking, you would want your circuits to work with minimum power, so that so that is the other way to improve upon the longevity of your device to work using the same battery technology. In other words, if you are able to improve upon all these power consumptions, you would allow, say, your mobile phones to consume lesser battery. That means it doesn't need to be charged um, instantaneously, or maybe it's the charging required by the batteries which are there in your mobile phones, its time would increase. The third type of uh, power consumption or power dissipation is your leakage power, which again is 20 to 50%, and it is kind of increasing because number of transistor is increasing. So as number of transistor is increasing day by day, so is the leakage power. So leakage power is going from 20 up to 50%, which is huge. So this is a major cause of worry when you are doing this constant miniaturization and trying to integrate more and more number of transistors into a chip. So more and more number of transistors would constitute more and more leakage current, because both the subthreshold current as well as the gate leakage current would be increasing with time. Okay, just a moment. So the overall power consumption in an inverter would constitute of dynamic power, the short circuit power, as well as the leakage power. So dynamic power and short circuit power is getting reduced by the day, but the leakage power is increasing by the day because the number of transistor uh, is per unit chip area is increasing by the day, uh, which is kind of governed by the Moore's law, which expects the industry to increase the number of or double the number of transistors per unit chip area in every 18 to 24 months. So the dynamic power, I think we need to wind up this part as soon as possible so that we can start with HTL part. So dynamic power is required to charge and discharge the load capacitance when the transistors are switched. One cycle involves a rising and falling output. We have already defined what exactly is rising and falling output. On rising output, charge Q is equal to C times VDD, which is required, and on falling output, charge is dumped to ground. So this repeat TF, where FSW is this frequency, so T times the frequency, so TF FSW times over an interval of time T. So this is how it is happening in a dynamic configuration. So power in dynamic configuration is given by this expression, which is C times VDD square FSW. So this derivation, I think you can do it. It's simple. If you have any issues, just let me know. And we have already talked about the activity factor. Suppose the system clock frequency is F, and let FSW is equal to alpha times F, where alpha is the activity factor. So if the signal of the clock is makes alpha is equal to 1, then we have already talked about if there is another signal, it is the ratio of the clock signal versus the signal itself. Okay, so if the signal switches once per cycle, alpha is half, and for dynamic gates, remember we have talked about static gates and dynamic gates. So in dynamic gates, switch either 0 or 2 times per cycle, while in static gates depends on the design, but typically the alpha is which is the activity factor is 0.1. So for dynamic gates, definitely it has to switch from height from 0 to 1 and 1 to 0. So the activity factor is generally half. The static power is power consumed even when the chip is in a steady state. Okay, so steady state basically means in sleeping mode or quiescent state. So there W by L, ratioed circuits burn. So moment we are talking about ratio basically means W by L ratio. Okay, so ratioed circuits burn power in fight between on transistors, and leakage draws power from normally the off devices. So in static configuration, the power is consumed when the the ratioed circuits burn power and fight for the on state of your transistors, while leakage draws power from normally the off stage of your devices, essentially transistors. So at the end of the day, we know all these different types of power consumption. So what are the methods so as to for a design engineer to improve upon this? What does that mean? Improve upon means to have the same circuit having same number of gates and same number of transistors and same functionality, but by using lower power. So how to reduce the power consumption so that the circuit functionality doesn't change, but the power that it consumes to get the same output gets reduced. So there are different ways. First way is to reduce the dynamic power. So that is done by these four parameters. So the first parameter is checking on the alpha parameter, which is the activity rate, and that can be done by clock gating or making into a sleep mode. The second one is the second method used to reduce dynamic power in an inverter configuration is by regulating the capacitance. So that can be achieved by using small transistors or short wires. The third way is to have the VDD small. Obviously that would help because VDD is directly related to your power. So how to have a suitable lowest VDD is another way to reduce your dynamic power. And the fourth and the final way to reduce your dynamic power is to have the lowest suitable frequency. How about in static power? To reduce the static power, one may have selectively used ratioed circuits. So that can be taken care by the design engineers working in say Cadence or Apple or Samsung and all those, and selectively use the ratioed circuit. So when they are designing it, they take care of W by L ratio of the transistor at various stages. If it is a single state transistor, then for PMOS and NMOS. Then selectively use low VT devices. So low VT devices is another important. So you would use the device engineers and the design engineers to work in collaboration. So those devices which have lower VT. So one way to have lower VT is at the process at the process level, means at the fabrication level, and the other one is by also playing with the voltage that you give to the other end of your transistor, which is the body. And the third way is to reduce leakage, and that can be achieved by some of the methods are having stacked devices, body bias, and having low temperature. So some places You may have temperature. So ideally, the temperature that we talk about is 300 Kelvin. So when we talk about lower temperature, it is going below that 300 Kelvin or 27 degree centigrade. And then body bias, we have already studied how the VT gets affected when you have bias given to your fourth terminal, which is body. So you have three terminals, which is source, gate, and drain. Okay, and then the fourth terminal is body. So by giving particular bias to your body, say in an NMOS transistor, you can actually change the threshold voltage, and that would help you to reduce the leakage current. So this is why knowing the basics of your transistors is essentially very important. If you do not know transistor, you cannot build up, because we are now going from transistor circuits and circuits to big modules of combination circuits, sequential circuits, and up the ladder into huge network of combination and sequential circuits. So generally speaking, for power minimization, transistor size plays a very important role. Okay, so if you want to achieve a higher capacitance from your lower capacitance, the width of the transistors goes from small to large. Width of the transistor, not the L. So whenever we are talking about transistor technology node, we are focusing on L, which is length, channel length. We do not talk in terms of width. So like as we are scaling down, it is going say point from say 180 nanometer to 90, 90 to 65, 65 to 45, 45 to 32, and so on. So that is the channel length, not the width. So here we are talking about the width. So it's a transistor is a three-dimensional structure. So it has length as width. So you need to visualize the 3D structure of the transistors. So to make the capacitance from low to high, you need to have the width of the transistor going from small to large. But this will have a opposite effect, in which you may require from higher voltage VDD to a lower voltage. So you have to balance out between the voltages that you supply, the width, and the capacitance to have a desirable performance of transistors in circuits, and in this particular case, the inverter. So I think we can skip this. This is something which is beyond. So ideally speaking, most of the times we are using CMOS configuration, but there are some better configurations which are based or which are offshoot of these CMOS configuration, which are generally studied in the advanced courses for your VLSI design. So those are like VSL and CPL and stuff like that. Okay, we shall not be touching at this moment in this course. So I end here. Now I talk about the last topic, which is your Verilog HDL. Can you see the slide? Hello? Class? Class is not with me. Hello?
Yes, sir.
Okay. Just a moment. What can you see? Can you see the slides?
No, sir.
Huh? Okay. So can you see it now?
Yes, sir.
Okay. So as I told you, this is the last topic that I will try to cover, which is the hardware introduction to hardware description language, and we will be specifically talking of Verilog. So, what is Verilog HDL? It is Verilog hardware description language. Basically, a high-level computer language that can be modeled, represent, and simulate to model, represent, and simulate a digital design. It has, as most of the computer language, it for your hardware designing, it has hardware concurrency, parallel activity flow, and the semantics for signal value and time, which is very essential to know the inputs and outputs. And there are a lot of designing examples using Verilog, right from Intel Pentium to AMD to Athenon to ARM processors. So all kind of chip designing industry use this. And thousands and probably millions of these ASIC designs use the Verilog hardware display. Remember, there's another very popular, so we are just talking about the most popular ones, which are used across the board. VHDL represents another high-level language for digital designs. So we shall only study Verilog, and its programming style is very similar to your C language programming. Okay, so this is the basic design methodology. Just give me a few 1 minute, and please note down this. So this represents the basic design methodology. Please note down. Now, this basic design methodology first is used by most of the design engineers and device engineers. So basically, people who are working in the industry. And remember, uh, these XDL, I mean, like as far as designing, testing, validation, verification of the chip is concerned, a lot of things are, in fact, a plethora of things are happening in India. And there are companies like from Intel to Freescale Semiconductor to Cadence to ST Microelectronics to Philips to Samsung, and I think now Apple and all these even um, other IT-based industries like Google and all are coming. And whenever they are making any kind of a chip, they need to design and they are using this. So basically, design engineering gives, or the end customer gives its requirement to your design engineers, and they start from the very basics. So they need to understand the requirements to get a particular performance of a desired module, which would constitute of very numerous of these combinational and sequential circuits, and also some analog circuits. So in real system, uh, digital and analog are not discrete, but they are integrated together, and what they call as the mixed circuit signals, uh, and but since we are doing the study, we are trying to bifurcate uh, analog and digital because it consumes a lot of time for us to understand. So whenever we are talking about digital IC design, we are talking in terms of Verilog, and for analog we have Verilog A. So that is that part can be dealt whenever you have done the analog IC design part of it, or CMOS based analog IC design. So here we are just focusing for the digital part. So initially you give, say you want to make a multiplier or a multiplexer or something like that, you give a particular that requirement to a designer, and then it basically what does the designer do? It goes and develops the so-called um, RTL model, which is inherent inside these tools, and synthesize the gate level model. Then it simulates via the bench, and then see whether the basic register transfer logic level models are there. So there is a simulation that is happening at the RTL level, the gate level, and at the final level, which is after the place and routing of these chips. So basically, you can imagine that it is a silicon wafer, and then you need to place all these different modules. Suppose yeah, your circuits has some memories, some kind of multiplexers, some registers, some kind of decoders, encoders, so on and so forth. And remember that circuit nowadays is so big and complicated that a small chip area may have say 1,000 to 1,000,000 times of different types of these combination sequential circuits. So you need to properly place and route them so that whatever whatever circuit is mostly used is closer to the other ones. Otherwise, it will create some delay. So of the uh, uh, placing of the right module in the, say, wafer, silicon wafer, is a very important part. And then routing basically means that you are having some kind of interconnects between different modules, which you may have produced or designed and manufactured discretely or separately. That needs to be done, and then the overall timing model needs to be. Yes.
So your screen is at slide one only. I think it's froze or something. It just displays yes. Okay. Now it's better. Thank you.
Can you see it now?
Yes, sir.
Yeah. So please note down. I was asking you to note down again and again. So basic requirements, and then you have this ASICs or your FPGAs, or your ASICs are your application specific integrated circuits. So here the computer science people are also very much involved because they are doing some kind of a coding, and then FPGA and stuff like that. Like in say IIT Delhi Computer Science or IIT Kharagpur and so on and so forth. So so they are doing these programming, and then so basically you all must have studied C, but you need to understand the basics of the circuit design and stuff like that. And at each level of at different modeling level, you kind of simulate and then test back, and then if it is correct, then you proceed, otherwise you go back. So basically right from the beginning you have a requirement, you go at the RTL level, simulate, and then if everything is fine, then you move forward, you synthesize to the gate level, else you kind of redesign and satisfy the model, and then you proceed further. And there are the test benches which are there to kind of helping you to simulate and um synthesize, as well as helping you in placing and routing. So at the end of the day, what you get is once you have designed, after going through these different levels, you synthesize, you place and route, and you get what is the application specific. So for a very particular application, like you want the chip in your lift which may be 20 floors or 10 floors, so which floors to give priority, which floors not to give priority, that can be designed both at the hardware level as well as the software level, and that can be application specific. That basically means that starting from scratch, but not necessarily. So or your FPGA, which where your hardware already available, and then you kind of program for things to work. So these hardware description language have modeling for your digital systems. So Verilog HDL is for writing models for of a system. Reason for modeling are requirement specification, documentation, testing using simulation, formal verification, and its synthesis. So you need to verify your circuits, you need to test them, you need to document them, and you need to check whether the required specification, required parameters, or performance parameters have been satisfied or not. And then their final synthesis. And the goal is to achieve most reliable design process with minimum cost and time. So design engineers, they are not doing something fundamentally at a at a very high level of mm, or a path breaking thing. They are just trying to help the existing knowledge and existing technology to go to the next generation, which would have better performance than the existing one, with a minimum cost and also size and time, and avoid any design errors. So domains and levels of modeling. So this is basically governed by.
Your screen again frozen.
Can you see this? Hello?
Yeah, sir. But we have missed fifth and second,
Did
third
you miss
slides.
slide you missed?
Yeah, sir.
Please note that. Can we move? Hello? I get no reply. Are you there?
Hello, sir.
Am I still on internet? Yes?
Sir, could
Okay.
you please present second, third slide again?
Okay, I think let's move. So, domains and levels of modeling. So, this is basically also defined as the Y chart due to Gasky and Kahn, who basically formulated this domains and levels of modeling. So basically, these have different levels and domains. So the different domains are the structural, the functional, and the geometric. And the different levels can go from the low level of abstraction to high level of abstraction. So in the first case, the lowest part would be, so that would be in terms of the functional part. So that would have at the lowest level the differential equation. Then it would be going to the next level of its hierarchy, which is the Boolean equation. Then it goes to the register transfer language, and then finally to the algorithm level. Okay. The other part would be talking in terms of geometric domain, in which the lowest level is transistor. Then it switches from transistor and goes up the ladder to gate, then to the register transfer, and then finally to the processor or memory switch. And third one being the lowest level, starting from the polygons, then to the sticks, then to the standard cells, and then to the floor planning. So the smallest design that you do is at the polygon level. Then you do the stick diagram of interconnecting and of the transistor itself. Then you make some standard cell libraries of say a multiplier or a multiplexer, and then you have all these major modules, and then you do the floor planning at the highest level. So the Verilog hardware description model specifies the relation between the input signals and the output signals. The HDL uses special constructs to describe hardware concurrency, parallel activity flow, time delays, and waveforms. So those are the important components. So what we expect, we design, and then we need to see the output instead of having a real-time fabrication of the device, because these chips are very small in dimension. Remember when all these things became important? It became important when the number of transistors went on increasing. That means the number of circuits and interconnects also started increasing. That means that you could not see actually with your naked eyes. The dimension of transistors are now so small and the interconnects are so thin uh, and there are so many layers that it is not physically like what you do in your lab, which are here. You have such a huge transistor in which nowadays the size of transistor which you see, one discrete transistor in your labs, that may constitutes of 10 to power 6 transistors in the chip which we use in the real time. So you can't see a single transistor, and then you cannot do some interconnects physically. So that needs to be done. First design using these kind of hardware description language, and up the ladder you are using the front end and back end of the electronic design automation tools like Verilog, or also sorry, like Cadence and Synopsys, and then you are actually giving it to fast for them to fabricate such complicated circuits, and which may have a million to billion, which is 10 power 6 to 10 power 9 transistors and beyond, maybe going up to 10 power 12. Yeah. So once you so before you send for fabrication, you would like to see that the hardware that you have designed for your particular application is robust and has a parallel activity, and the time delays are kind of there is a is minimized, or there is a mitigation in that, and the final waveform is as desired, so that the performance matrix of your digital circuits is giving you maximum output. Okay, so let's start with a very log code for an AND gate. Please note down. Hello. So it has module. So we are talking about different modules, and gate. So this AND gate would have an output Y and input X1 and X2. So you write input X1 comma X2 and the output is Y, and then you're ANDing this part. So with Y as your output and X1 and X2 are input. So Y is your output and X1 and X2 are input. So, and then you end the module. So this is the first example of a Verilog code for a simple AND gate. Next example, say for a half adder. So you give a module, the output is sum and carry, while the inputs are A comma B. Okay, and then you also have a output which are wired, which is C output bar. So first, to know, to construct this module, you need to know the basics of designing of your half adder itself. So half adder would have a XOR gate, a NAND gate, and a NOT gate, which needs to be wired. Okay, so XOR gate, so the wiring between these different types of gates is done by the third statement, C out bar. and the different gates are G1, again the output and input sum, comma, A, comma, B. NAND gate would be C out bar, comma, A, comma, B. And NOT gate would be C out bar, sorry, C out, comma, C out bar. And then you end the module. Okay? Hello? Hello? Class?
Yes, sir.
Okay. So to realize this module for your half adder, you need it for a full adder and higher the order of your combination circuits or even a sequential circuit. Like for a D flip-flop. So module flip-flop, you have Q and then data in, clock and reset. So inputs are your data in, clock and reset, and Q is your output. So here, when it works, when you have a clock pulse, which is positive edge. So begin if your RST is equal to 1, Q equal to 0, else you have the data in. So this is how a D flip-flop works. So you need to know the basic design and then implement this. You end and then end the module. Verilog with a structure-based module, like for example, you have a MUX. So structure modules are built from the gate primitives and or other module which are pre-existing. So they describe the circuit using logic gates, much as you would see in the implementation of a circuit. So you need to identify gate instances, wire names, delay from A to B, A to F or B to F, where A, B are your input signals and F is the output signal, and select is when you are doing it for a simple mux. So you should be knowing mux. So module is your mux, if F is your output, and A, B and the select line is for your input. And then what you're doing is basically you are having the AND gate, which are essentially odd at the final state. So you need to identify wire names, delay, and gate instances. So you please note down this one. This will also help you. Be the same but on a similar pattern. Now we go further because I'll give you one more minute. Any questions? If not, then let me move further. So these are like gate level models, and need to model the gates, you need to talk in terms of function and delay. So in terms of function, generally hardware description language have a built-in gate level primitives. Verilog has NAND, NOR, AND, OR, XOR, XNOR, NOT, and some other which are present or inbuilt. The gates operate on the input values, producing an output value. So typical Verilog initiation is and then instant name, output, and inputs. Now we go to the how to build a test module. Remember, initially we talked about the test module when we talked about the flowchart of designing a circuit. To construct a test module for your design, develop your hierarchical system within a module that has inputs and output called design here, and develop a separate module to generate tests for a module test, and connect these together with another module in a test bench. So this is giving you an example of module test bench where you are having a wiring between L, M, and N, and design D and test L and N. So it starts at the initial beginning. Then you have module design A, B, C, input A and B and output C. And you need to module test Q and R, where outputs are Q and R. So you have an initial beginning which drives the output with signals. So the test bench is the final piece of your hardware which connects the design with test so that the inputs generated go to the thing that you want to finally test. So it's basically, you can say, calibration or examination of the chip that you have designed. So module test generates input for module half adder and displays changes. So module test generates input for module half adder and displays changes. So module for half adder was designed. You can see. Okay. And then your test bench was also generated. So together, this is what you are having. So on the left hand side, you are having module test bench and module for half adder. And on the right hand side, you have module test for your adder as a whole. I think that's about it. It's just explaining the function testers of function of this tester and the test generator and stuff like that. So other important things that you can do is here. I think it's almost just 5 to 10 minutes are left. Around 10 minutes are left, so I would like to wind up. So extra commas print spaces. This percentage B is binary also, percentage H and percentage D is there. Then new line automatically includes this thing. So I think this may not be required. Another important thing which you should be knowing, so that is basically for test pattern. I think brief idea is good enough. So we will not be talking about, we will just be talking about simple programming of basic, so that will be part and parcel of your examination. But you should be knowing what is structure and behavior model. So structure model just specify primitive gates and wires, the structure of a logical netlist, and one should basically know how to do this. The other one is behavior mode, like a procedure in programming language, which specifies a module in a Verilog with inputs and outputs. But inside that module, one can write code to tell what you want to have processed, not what the gates to connect to make it happen. Okay. So why use behavioral models? Because for test benches modules to test structural designs, and for high level specification to drive the logic synthesis tool. So these model hardware at different levels or abstraction, next different levels of abstraction in description and simulation, able to model hardware concurrency, so that you have a robust circuit, and support hierarchical decomposition, availability of ASICs uh, for your foundries to make the chip. So here there is a kind of a systematic hierarchy, and at behavioral level, structure level, and geometrical level, which we have talked in detail. And this Y chart is very important, starting from the low level up to the high level, and it is basically these three different level that we are basically concentrating on. The one is structural, one is functional, and one is geometric. That ends with the course. So there will be a full question on the HDL part. I think the questions, whatever has been covered till now, would have given you a brief overview, or in some cases a detailed overview of the transistors and basic circuits, for which which can be actually designed and translated into real chips. Yes, any questions? Any questions? Manali, Manas, uh, Premlata, Mansa, Anil.
So
Hello?
would so would midsem 1 and midsem 2 syllabus will be there also in our exam.
Of course.
So is there any weightage for them? Like we have already
Yeah, I mean, like, yeah, so since we could not cover a lot of things in the final stage, so the final stage as in like our post your midterm exam, so we will have, I mean, I cannot, maybe one or two question based, obviously there would be two questions, or maybe half of the paper would be post your midterm, the other half would be from the beginning. So 40 to 50% of your questions would be from the portion that we have been able to accomplish in the time after you have finished with your midterm exam, and the rest, which is 50 to 60%, would be from the time we started this course. Any other questions? So there will be most probably 5 questions to 6 questions, uh, and it would be scaled down to 50%. So final examination is always of 50. So the weightage is 50.
Okay, sir.
Hello.
Okay, sir.
Any other things? Any other queries, questions? So whatever has been done till date, there will be a question. There is no doubt about it. And I think there may be 2 to 3 questions uh, from the part which we have done post our midterm exam. And I think the reference book is, I've already talked on devices, your Streetman and Banerjee for digital design, to know about all kind of different types of design you referred to, and also for your HDL you refer to Morris Mano digital design, and also this Jan Rabe for digital CMOS IC design, and lecture notes from NPTEL, lecture notes from Professor from IIT Roorkee, and my lecture uh, right from the very beginning, because I have sorted out from various sources. Uh, and what else? I mean, like, if you have any other question, just let me know. Remember, until unless you understand MOS transistors basics, it will be very tough for you to appreciate anything in this course, or those of you who want to pursue this VLSI design, whether it's analog, digital, embedded, anything, it will be difficult for you to capture that. So all these, or even in terms of designing through synopsis, cadence, and all kind of, so all the industries are using these tools. And if you see like spice and all that one of the professors in fact has given, that is a free available, but that is not actually as relevant or as much in use in the industry as your Verilog or synopsis or cadence and so on and so forth. So those are like, you're working on the same type of tools, having theoretical knowledge as you would use in the industry if you pursue this line. So most of the guys who are passing out from all the big standard universities or institutes like the IITs, triple IITs, NITs, they they have an upper edge essentially because they have hands-on on all these design. They actually do some projects and they do say thesis also on that. So like when I was at BITS Pilani, they used to do all these things both at MTech and BTech and even PhD level, but then they used to go for the internship in Intel and Samsung and all these other places. Same thing was true from Triple IT, and they used to go for mostly Japanese-based Fujitsu and some of the other types of companies, which was so. And then all the other companies also run the same. But uh, those who want to pursue this as a line and they want to get into embedded or VLSI as a whole, this knowledge and exposure to tools and designing these circuits is very essential, both for embedded as well as VLSI. You're talking about, yeah, even computer architecture, because architecture is a part and parcel of the overall VLSI design. So yes, hello, are you still around?
Yes, sir.
So Samata, you have some question? You've just arrived.
Sir, I was just not arrived now, sir. I have been before, sir. Like network issue came now, sir, again.
Okay. Any questions?
No, sir.
Okay, then good luck. See you on Tuesday. And if you have any queries or any questions you want to talk post examination, before examination, you are welcome. And those who want to continue further, because I think there was not enough justice to this course, essentially because of time constraint and also because of the resource constraint, because I think had you had more number of these synopsis tool or cadence tool in your labs, things would have been better. So there would have been a lab component. At least, we cannot go for designing a complete module, say a complete small module of a project would take a longer time. So that people generally do as an MTech level thesis. So like at BITS Pilani and BTech's fourth year students or MTech second year students used to do a joint project with the industry or with some other global academic institutes or with us as in like with the faculty itself standalone, and that used to actually help. Until unless you do a hands-on, you try to think, you make better design, you get better parameters, performance parameters, you would not be able to appreciate. So I mean, like, the designing part, the testing part, and the validation part is happening in India in a big way. a lot of jobs, and they need good designers and good testers and good verification validation engineers. What is lacking is fabricating of those chips, and that also I think over a period of time may just arrive in India. So that would be on the IC or VLSI technology or VLSI fabrication, but designing is already happening in a big way. So, and then they take the designers who have that master's degree. I mean, like because there are too many bachelors, and then they are not exposed. They are exposed to so many courses, but they are not specialized. So you must have seen in all the IITs and all, they give gate and they go for a VLSI program, or so those who kind of enter into such programs have very good gate scores, or they are in the top ranking. So that is their first, especially from EE, electrical instrumentation, electronics and communication, even IT. That is their choice number one. So within few hundreds, most of my students that I know who kind of went for their MS program in the IITs or outside India, they had very good score because that was quite in demand. Yeah, nowadays, I mean, like if we talk towards computer science, they will be talking about AI and machine learning and stuff like that. So yeah, that's a different domain altogether. But yeah, switching over, I mean, like if you talk of biggies, um, electronics and communication are like having a lot of overlapping, right, from computer architecture to. So yeah, all you need to study is a couple of more courses like data structures and algorithms, so you get into big data and everything, and then some courses on your. Yeah, any questions? Otherwise, we can log out. Thank you. If no questions, thank you and good luck.